Oh, welcome to another week, folks. So, a little bit of good news. Next month at this time, we'll be in the last week before finals week. So, yeah, blink and this year's going to be all finished. So, anybody know why it is that nobody is really friends with Dracula? Why doesn't he have many friends? Poor guy. I like that. He's such a pain in the neck. Why is it that, in physics here, a lot of times we talk in terms of the metric system, when, in everyday life, we're used to talking about things in feet and inches and pounds. Why is it, do you suppose, that Americans will not quickly change to the metric system? Any thoughts on that?
Because we're stubborn.
Quick on their feet, stubborn, looking for something different. Good guesses, though. It would simply cause mass confusion. If you're going from kilograms to pounds, it's a lot of confusion. Probably should have gotten that one out of the way first, huh? Okay. So, we've got a momentum test coming up tomorrow. So, today is our review day, and you might want to take some notes down and write this stuff as we go along. If you don't have your formula sheet with you, I have some extras up here. Please feel free to grab those. Also, of course, remember that your egg drop project is due on Wednesday. So after the test, we are going to be dropping those eggs on Wednesday this week. So page 1, you're going to be answering in one of 3 ways. A is greater than B, A is less than B, or A is equal to B. So let's see what you're going to have to deal with here. As you probably guessed, this is going to refer to momentum. So let's just say we have object A. And object A is maybe a 2 kilogram mass. Perhaps it's moving to the right at 4 meters per second. And then you've got object B. This will be a different mass, maybe just 1 kilogram. Also moving at 4 meters per second. If you were to compare the momentum of these two objects, how would you do so using one of these 3 explanations? Is A greater than B, A less than B, or A equal to B? Yeah, exactly. A is going to be greater than B because, remember, momentum is mass times velocity. So 2 times 4 is 8. 1 times 4 is 4. 8 is greater than 4. Therefore, the alligator eats letter A because it's bigger. Now, let's say I take this one step further here. Now I've got an incline. You've got fond memories of these babies, right? So we'll say that we've got the 2 kilogram mass right here. And it has a certain momentum when it reaches the bottom. And then, of course, we've got the 1 kilogram mass. After the 2 kilogram mass rolls down, we do the same thing with the 1 kilogram mass. So compare the momentums of these two objects when they reach the bottom of the incline. So take about 10-15 seconds, think about how you'd respond, and then we'll talk about this one briefly. Any thoughts on this one? This is a bit trickier. So, momentum is mass times velocity. So we know the masses aren't going to change. So the real question is, which of these two objects is going to have the bigger velocity at the bottom? Does anybody know the answer to that question? What about if I just let them go from a certain height? How fast would they be going when they reach the ground? The same speed or different speed? The same speed. And the same thing is going to be true if you're on an incline. So both of these objects are going to reach the ground at the same velocity, which means that the 2 kilogram object, which was letter A in the first example, we'll keep it letter B here, or letter A. So that means this object would have the greater momentum at the bottom of this ramp. So once again, A would be greater than B. So from this, make sure that you remember if both objects are released from the same height, whether that is actually dropped and they're in free fall, or whether they're going down an incline, they'll have the exact same velocity when they reach the bottom of it. And that'll guide you to the correct answer in these questions. So the next example, if you've got your formula sheets out, go to the motion box and look at the very, very bottom of the motion box. It says F versus T, area trapped, equals I. You need to know that because there may or may not be a force versus time graph on the test. Go ahead and draw that. See if you can use your formula sheet to figure out what the impulse is as a result of that graph. Bless you. All right. So does everybody, even if you didn't have enough time to run the full calculation, does everybody see what you would do with this to calculate impulse? Okay, so on your formula sheet, it says force versus time, area trapped equals I. The I stands for impulse. So if I want to calculate the impulse of this graph, what I have to do is I have to calculate the area that's trapped by it here. So I've got basically two shapes that I need to find the area of. I've got a rectangle here, and I've got a triangle there. So if I can add up the area of those two shapes, I automatically have my impulse, or my change in momentum of this scenario. So base times height, 10 times 5. So that would be 50 for that shape. And here we've got, again, base times height, but because it's a triangle, we got to go 1/2 base times height. So that would be 25 divided by 2, which would be equal to 12.5. So 50 plus 12.5 is going to be equal to 62.5 for your total impulse. And the units on impulse are the same units as momentum, because it's just change in momentum. So kilogram meters per second would be what you do with that. Questions here? Yes? For here? Well, for the triangle here, our base is just from this position to this position. Yep. All right. Did I do the rest of the math right? Okay, good. So if you do have a graph, that's how you deal with it. You can have a negative impulse in the same way that you can have a negative momentum or a negative change in momentum. So if this would be below the 0 point, you could have negative values here. Make sure you're aware of that. All right, next up, let's do a couple thought experiments here. I'll give you a little bit of time to draw that in. What we're going to do right now has to do with the multiple choice portion that will be on page 2 of the test. So for this question, the 4 kilogram object begins at rest on a frictionless surface. Meanwhile, we've got this ball that is going in here at 1 meter per second. It's flying through the air. It has a mass of 0.5 kilograms. Can anybody tell me the final momentum after this ball has an inelastic or sticky collision with the 4 kilogram mass? What is the momentum that these combined masses are going to have as they move off to the right? Can anybody tell me without doing any fancy equations here? 0.5, absolutely. Because momentum is going to be conserved before and after a collision. So if before the collision, we've got a total momentum of mass times velocity, 1 times 0.5, that's equal to 0.5. If the total momentum going in is to the right at 0.5, that means after the collision, both masses must be moving off with a total momentum of 0.5. So you don't need to do any big equations here to figure this out. You just got to remember original momentum equals final momentum. That's absolutely true. How about this? These objects have the same mass. This one is coming in with a momentum of 1 kilogram meter per second. After colliding with this mass, which is the same mass, this one moves off to the right, and this one stops. It is no longer moving. So what is the final momentum then of this mass? You don't need one. We'll say this one's coming in with a momentum of 1, and then after colliding with this mass, this one stops, and then this one starts moving. What would be the final momentum of the second mass there? Yeah, just 1. Because all the momentum would be transferred from one to the other. If we begin with a momentum of 1 to the right, we must end with a momentum of 1 to the right. That's what conservation of momentum is all about. Now this next one, I want you to think about a little bit, because it's just a little bit more tricky here. But you do need to know this. Once again, there is no friction, so this looks pretty much just like the first example. The only thing is that after this object collides with the 4 kilogram mass this time, this object bounces back to the left. So it collides with the 4 kilogram mass, and then it bounces off to the left. Now, for this particular scenario, then, the question is going to be, what is the momentum of the 4 kilogram mass? Is it going to be equal to 0.5? Is it going to be greater than 0.5? Or is it going to be less than 0.5 kilogram meters per second? So think about this for about 30 seconds, and then we'll talk about it. It is just a little tricky. So would anybody like to hazard a guess here? This might be the most tricky question we go through today. Let's do a vote. I just kind of want to see where your gut stands here. So again, when this object comes in, it has a momentum of 1 times 0.5, which is 0.5. Then it collides with the 4 kilogram mass and it bounces to the left. So, after that collision then, what is the momentum of the 4 kilogram mass? Is it 0.5? Is it greater than 0.5 or is it less than 0.5? How many votes for it is equal to 0.5? It is greater than 0.5. One maybe. It is less than 0.5. Okay, so let's take a little bit closer of a look at this and we'll talk about it here. So, we know that at the beginning, we've got a total momentum to the right of 0.5. We'll say green means momentum. So that means after the collision, we still must have a total momentum of 0.5 to the right. Now, after this ball collides with that mass there, and it starts going to the left, now this has kind of a negative momentum because it's moving in this direction. So if the 4 kilogram mass only had a momentum of 0.5, then the total momentum of the entire system together would be less than 0.5 because this mass is moving to the left, which is the negative direction. Are you with me so far? Okay. So what that means then is this mass must have a momentum that is greater than 0.5. Because overall, between both objects, when you add them together, you have to have an overall momentum of 0.5 to the right. So let's say we had enough numbers here to figure out what this object's momentum was going to the left after the collision. Let's say after the collision it had a momentum of 0.1 to the left. That means that this 4 kilogram mass after the collision would need to have a momentum of 0.6 because 0.6 minus 0.1 is equal to 0.5. The total momentum of both objects after the collision must be equal to 0.5 to the right. So that's kind of the reasoning for that. Does that make a little bit of sense? Okay. Let's do something easier. So yeah, when we say momentum is conserved, it's not just for one object. It's for the entire system. It's for all the objects that are involved in the scenario. There is a 1 kilogram object. It is traveling down at 10 meters per second. And then it hits the ground and it bounces up with a velocity of 8 meters per second. Go ahead and calculate the change in momentum, please. Anybody get 18?
You just. No, man.
It's okay. So, yeah, change in momentum is just final minus original. So, mass times final velocity minus mass times original velocity is how we'd calculate this. So we know the mass is equal to 1. So 1 times the final velocity, final is going to be 8, minus the mass times the original velocity. What's my original velocity here? And more specifically, negative 10. You must take negative directions into account here. Very good. So when you do this math, 8 minus negative 10 is going to be equal to 18. And of course, this is also equal to your impulse, because impulse and change in momentum are the same thing. All right. 3 more examples. Let's do this. This is a pitching machine, believe it or not.
It looks like Big Bird.
It does. We can say it's Big Bird. So this is Big Bird. And Big Bird is spitting out baseballs from his big mouth. And here's one of those balls coming out right now. And this ball has a mass of 100 grams. And what we want to know is how fast that ball is exiting Big Bird's big beak. So the other thing we know is we know some information about Big Bird here. So I guess for Big Bird, we'll use double B's. So this is going to be equal to 100 kilograms. And then the velocity is going to be equal to negative 1. So using this information, we got to figure out the velocity that the ball has as it exits. So just take about 60 seconds, try and get this at least set up to solve, and then we'll go through it together. We'll get to the last 2 examples then. Alright, again, if you didn't have time to solve, that's fine. Hopefully you at least got something set up with the equation. Best way to start this, original momentum equals final momentum. So both of these objects start from rest. The ball begins inside, and Big Bird starts at rest too. He's just standing there. So what that means then is that original momentum is going to be equal to 0. And that's what's really going to make this nice and short for us. So now we got to figure out what the final momentum is going to be equal to here. So we've got mass of Big Bird, velocity of Big Bird, plus the mass of the baseball, velocity of the baseball. So the the final velocity of Big Bird as he slides off to the left here, we're kind of assuming that this is an icy, mostly frictionless surface. So he's sliding to the left at -1. So what I'm going to do is I'm going to take his momentum, move it to the left. So that means we have the mass of Big Bird, which is 100. And then the velocity is that -1. And then over here, mass of the baseball, 100 grams. Do we leave that as 100 grams? No. What's the conversion for this one? Close. 0.1, because we divide grams by 1,000. So 100 divided by 1,000 is 0.1. So that's 0.1 times the velocity, which we're looking for. So if we're going to do this, then what we got to do is we got to divide both sides by 0.1. And actually, as I move this whole thing over to the left, the whole thing becomes negative. I forgot to do that. So when we divide both sides by 0.1, this is a positive 100 because the negatives cancel out. Divided by 0.1, giving us a velocity of what? 1,000, right on the money. And that's what we would have for the final velocity of the baseball there. So whenever you have something where both objects begin at rest, remember that you can just get rid of the entire left side of that conservation of momentum equation. If your original velocity is 0, that entire momentum starts out as 0. And of course, we've got our two collisions that we have to take a look at here. I think I'll get these both on the board so you can have some time to work on them, and then we'll just do them with the last 5 minutes of class here. So, example 1. So this is a 150 kilogram cart. This cart is slightly larger. Actually, it's quite a bit larger. 400 kilograms right here. And they're going to be coming together like this and colliding. The original velocity of this guy is going to be equal to 30. Original velocity here is going to be -20. And these two masses are going to collide inelastically. They're going to stick together after that collision. So let's just go ahead and we'll solve this one together. So if we want to figure out the total velocity of the combined masses after they smash together, we just got to approach it the same way we approach every single other momentum problem. Original momentum equals final momentum. So I'm going to call this mass 1 because its mass starts with the number 1. I'm going to call this mass 4 because it starts with the number 4. And we'll just kind of write this out here. And this is how that would look based on the equation for an inelastic collision on your formula sheet. So, in order to solve for that final velocity, we just have to get that final velocity all by itself. And we do that by dividing both sides by the sum of the two masses. So, I'll just put the numbers in here. So this is this right here, That's that. And then I got to divide both sides by the sum of the masses. 400 plus 150 is equal to 550. And that's going to get us that velocity. And if you run that calculation, you should end up with negative 6.36. And that would be your final result there. These are probably the easier collisions to deal with in terms of your collision equations there. Questions on this one? All right, last one. So here's our beginning information. Calling this mass 1, we'll call this mass 2. So this is going to the right at 70 meters per second. This is going to the left at negative 80. We also know a bit of information about after the collision. We know after colliding, the impulse on this object is equal to negative 100,000 kilogram meters per second. So knowing that information, I would want to calculate the final velocity of object number 2. So let's go ahead and run that calculation here. These objects are bouncing off of each other. This is an elastic collision. So what I got to do is I have to use my elastic collision equation, but I do already know the impulse of this object here. And if I know this impulse, what else do I know? The impulse of the other object. So if I know the impulse here is equal to negative 100,000, that means my impulse of object 2, or my change in momentum of object 2, is equal to positive 100,000. So I can set this equal to the change in momentum of object number 2. So final momentum is going to be the mass times the final velocity, which we're looking for, minus the mass times the original velocity, which was negative 80. So now it's just a matter of calculating the velocity from this equation here. This equation right there. So let's do this. I want to get this to the other side. So let's see here. 800 times 80 is 64,000. And that negative is going to cancel out that negative. So then when I pull it over to the other side, it's going to become negative again. So that's going to be 100,000 minus 64,000 equals 800 times the velocity of object number 2. So we just got to do some subtraction and some division here. So this we've got 36,000. And let's see. It's equal to 800. And so V2, I have a final velocity of 45 meters per second there. Again, folks, when you're running these calculations and you see these problems, don't make them more complicated than they need to be. Original momentum equals final momentum. You can approach just about every problem in that way. If you have any extra questions or you want to go over some more examples to get more comfortable, feel free to see me after school today, before school tomorrow, whenever you can. Otherwise, that's that.